Hello. Hi guys, good morning. Welcome back to a new video. Ki hal chal? I hope you guys are doing good. In this, we're going to see problem maximize sum of weights after edge removals. It's actually hard, and if you don't know, it's actually hard. Now, apologies for the video being a bit late. Actually, I am selling a bit of stuff, so people were coming in, so I had to entertain them, so called to sell my stuff. So yeah, cool. Let's start off. It simply says that we are given an undirected tree we have for n nodes you will have n minus 1 edges. That's a simple tree. Now it's undirected, so there is no directed edges. I have n nodes, each node is numbered from 0 to n minus 1. Standard tree. Now the thing is that I will also have edges. These are representing weighted undirected edges. So these are weighted undirected edges, and also my task is to remove some edges. 0 also can be. Now, how I will remove it, or what I can do for removing, or why I have to remove it, is that each node has an edge with at most k other nodes. So, a node can have at most max to max k other nodes. So, I have k as 2 here. So, this node is currently having 3 neighbors or 3 edges which are spawning from him. He should only have at max 2. He can have 0 also, he can have 1 also, but at max 2 will be there. Now, to achieve that, what you can do is you can remove some edges, right? But you have to remove such that the sum of weights of the remaining edges is maximized. As you can see in this example, because this was violating the condition, I had to remove an edge. Either I could have removed this edge also, I could have removed this edge also, I could have removed this edge also, but I removed this edge because deleting it will still make my sum of weights to be as max as possible. Cool. Now, we have to return the maximum possible sum of weights which we could achieve. Now, whenever we read this kind of stuff, now the first very basic thing which comes to our mind is, Aryan, let's go and try greedily. Obviously, because if you see this example also, the weight was 2 here, which was the minimum. And I realized it is violating this specific weight 2, having both the nodes attached to it, or this specific edge having weight 2, having both the nodes attached to it. I realize, okay, this is good, but this is violating. Simply remove it. That's the best case thing, na? Why not remove it? Usually people think of it, but then they also realize that, okay, it's not true. Now, why? Because simply take the example like this. Again, it's very easy to come up with this example, because here I realize k is 3. Every node can have at max 3 neighbors. For both the nodes, I have having 4 neighbors. So I have to remove one node. But I realized, okay, I will go greedily, remove the node having the minimum weight. So I will remove this edge. Then I realize, okay, this is good, but this is now violating. I remove this edge. In total, I removed edges of weight 6. But if I could have simply removed this edge 4, I could have achieved my corresponding answer. Thus, I would be only required to remove a weight of 4. Thus, greedy would not work here. Now, in these cases when greedy don't work, then what? Obviously, in these scenarios, try for all the possibilities. What is the possibility here? Possibility is removing each edge. Obviously, remove for every edge. Go and ask him, bro, can I remove you? Can I not? Should I remove you? Should I not? So I will remove it or I don't remove it. I will go to every edge and I will ask it, do I? And it's simply now a knapsack problem, that should I remove it? Should I not? Do I remove it? Do I not? Like this. And obviously in this, you obviously know that's a very standard stuff. Whenever you have do it, not do it, take, not take, you have to apply a DB to memorize it. But it seems so simple so far. You know what's going to be applied, but the biggest factor is how will you apply it, because there will be multiple cases which come up right now. See, I took this example, and here as you can simply see my n3. Obviously, see, there are two things. We will apply DP. We know that we will apply simple recursion. Simple recursion for a tree is nothing but a simple traversal. So we are referring a simple tree traversal, which is a simple DFS for us. Now, if I'm doing a simple DFS for any node, I would only be, because again, when I say DFS, which means I am at N1, it goes here, then goes here, then goes here, and then here, and then here. Ultimately, what's happening? Ultimately, for any node, I am going on to its neighbor, which are the children, right? Because I cannot go back to parent and then again try the entire DFS, because that will make it O of n square. I have to not do it O of n square, I have to do it O of n log n or O of n. Which means that for this node, for these neighbors, I will just simply go and tell them remove, not remove, remove, not remove, remove, not remove. What I mean by that is remove this edge or not remove this edge. Then what's the weight or what's the score? Remove this edge or not remove this edge. Then what's the score? So this is how I can actually go about it. But the fact here is that we also have taken consideration parent factor, which we have not taken in consideration. Now, why parent factor, all that stuff, we'll come on to it, but that is primarily required because I'm referring neighbors. Whenever I'm referring remove it, right now I will tell exactly what to remove and when to remove, but to remove something, I'm only checking the children. It doesn't make sense because neighbors are the things which needs to be removed. So technically, I have to also take in consideration two major things. Remove some nodes, obviously you have to do it, and don't remove some nodes. But when I say remove some nodes, the question firstly will come is which node to remove and then how many nodes to remove. Now, Aryan, how many you already should know, right? You have, let's say for one node, you have 5 neighbors. You want to require k as 2, so you will remove 3. Isn't it simple? It could have been simple considering you were dealing with everything, which means you are dealing with parents also. But in this case, you only deal with children, not the parents. So what happened with the parent? I would never know. Considering the parent would have already been removed, there is no requirement of removing more children. So that is the reason. How many to remove is also a question. Which one to remove will also still be a question. I will tell you why. Now, firstly, let's jump on to how many nodes to remove. When I say how many, I simply am referring if I am at n3, my k is let's say 2. As you can simply see, I have 1, 2, 3, 4, 5 nodes. I should remove ultimately 3 nodes. But I am doing a simple DFS traversal, so I can only look at my children, not my parent. In that case, I should somehow take in consideration the significance of my parent. So what I will do is, I will maintain a variable saying is parent edge removed, which when I am doing a simple DFS traversal, I will also be putting down or telling the person down that am I removing this node? If I am removing, sorry, am I removing this edge? If I am removing this edge, I will pass down to my child n3 as this will be the node n3 whose is the parent edge removed is true, or I should say 1. And if it is not removed, if it is intact, then okay, obviously I will pass it is removed as 0, not removed. Why this will be helpful is because I will simply, again, in my simple DFS, simple solve function, again, why I wrote solve here, because it's a memoization case, but it's actually simply a DFS. I will simply go into every node, but the other parameter which I'm kind of maintaining parallelly with it is a parent edge remove or not. So as to maintain the edge between node and its parent, because that edge will help me to know how many edges I should remove from my children, right? Because in this case, the k is 2, so technically I should remove 3 edges in total, but I could only see 4. So technically I would say that, oh, it is 2, I should remove, I have in total 4 children, so I should technically remove only 2. But this, I should remove only 2 will be applicable when this thing may or may not be removed yet. Which means that actually number of edges to remove will rely on for a specific node, how many neighbors it had, obviously how many nodes it needs to come to, or how many neighbors it needs to come to ultimately, and is the parent there or not. Which means that for this specific node, it had 5 as its neighbors. I want to come to 2. Which ultimately mean that I should remove how many children? This will say remove 3 children. So out of these 3, n1 and any1, again neighbor 1, neighbor 2, neighbor 3, neighbor 4, I will have to remove 3 children. But what if this parent would already have been removed? Then out of neighbor 1, neighbor 2, neighbor 3, neighbor 4, I would be only allowed, or I should be removing only 2 children. That is the reason, also taking consideration, is parent removed. If it is removed, then decrease your value. If the parent is already removed, then -1. Then you are only required to remove 2 neighbors from your children. That's it. That is the reason how I will be firstly computing how many edges actually to remove. And again, these are edges to remove from your children, because you are able to only iterate on your children. Now you know that how many edges to remove, but still the question which we left off is that which of these neighbors to remove. That's a question still, right? Yeah, that's a question. Let's see how we will come up with it. So I took the same, let's take a smaller example, a smaller subtree. In that, as I told you, for every node I will be simply going and traversing. Now I will compute, not remove or remove. I will compute for every node, not remove or remove. Again, not remove or remove. What this tells, not remove or remove. This not remove or remove tells what if I could have removed this specific edge, then what could have been the corresponding score. If I would have not removed it, then what could have been the score. Same way, NR2, not remove 2, not remove the child 2, is ultimately saying this edge, if I would have not removed it, then what is the score. R2, if I would have removed it, then what is the score ultimately. Now, if you know this, my question was, how will you figure out which node to remove here? In this case, I have these 2 edges, and I am telling you, one of them you will have to remove. Tell me which one you will remove. In that cases, build some relation. Okay, what's the relation between them? So I'll take both the cases. Let's take, in first case, I remove R1, which means I will not remove R2. I will keep R2. So the score will be R1 plus not removing R2. Right? What if I remove R2? Okay, I remove R2 and then I will not remove R1. So score will be not removing R1 plus R2. Now my task was, how will I identify that which one to remove? For that I have to take an assumption. Now my assumption is that let's say removing R1 is good. Let's say removing R1 is good. When I say good means giving me higher score, which means that I am assuming that if R1 removing is good, so obviously this score should be higher than this score. In that case, this score is higher than this score. I will just simply try to bring the variables on the same side. Now, bringing variables on the same side is a very standard technique which helps us to build a relation in linear terms rather than in n square terms. So I will bring the variables. So I will bring nr2 here by bringing r2 here. So it will become nr2 minus r2 is more than nr1 minus r1. Now, going back to the assumption, I assumed that removing r1 is good. If removing r1 is good, he brings me to a relation that removing that specific node edge is good, whose difference is smaller. Difference between what? Difference between not removing and removing. Whosoever difference is minimum or is lesser, that specific node edge is good to remove. Thus, it helps me to figure out that if I had, let's say, these 5 children, I will sort them on the basis of their not remove minus remove values. And then, as in the previous step, I told that now I have number of edges to remove, actually remove in my children's. So I would easily say that if the number of edges to remove in my children is 2, so out of 5 children, when I sort it with the increasing values of nr minus r, which is not remove minus remove, then starting 2 children, I should remove it because they have the minimum corresponding nr minus r value, and minimum corresponding nr minus r value results in the highest score, So I will simply remove the starting 2 number of children. When I say remove, I will simply take the contribution of these 2 children only for remove. So I take the contribution by R1 plus R3. Only take the remove contribution. But for the others, I can do anything. I'm not saying that I will not remove them. I'm saying I can do anything. Because the question says have at most k nodes. Right? If my marzi, if my will, I will probably remove all the nodes. So for the remaining ones, you can take both not remove or remove, not remove or remove, not remove or remove. But make sure you want to maximize your score. So take the maximum of, for child C4, take the maximum of not remove and remove, take the maximum of remove, not remove and remove, take the maximum of not remove and remove. for these childrens. But for them, I will always and always take remove because I will have to remove them. Cool. Now, that is the entire crux and the entire explanation for this problem. Let's see the code. Now, to look at the code, you will have to understand everything I actually told you, but I will actually also tell. Again, the corresponding C++ code I actually missed, but okay, I'll put the link of my solution. You can just simply go on to GPT and convert it, or I'll also put the link in C++ also. Now, the code simply says, firstly, I make an edge class. Now, this edge class is nothing but corresponding neighbor and weight. This will help to build my corresponding graph. Then I initialize my global variable of dp, my graph variable, which is the adjacency list, and also my k, global variable k, input. Then I went on to all of my nodes and tried to build the corresponding graph. Simple adjacency list for any node which is u. Simply add a v comma corresponding weight as a edge. Again, I have made an edge specific as a class, right? With this, I have now an adjacency list, which is the weighted adjacency list. Now, initialize my dp with the value of -1. Simply go and call my dp with what value? Obviously, I will start off with any random node, taking node 0 as a random node. His corresponding parent can be anything, but I have to also take one more variable, which is parent removed? For the very beginning, which is the root node which I'm considering, there is no parent removed also, so by default value 0. And his parent is also nothing, so -1. Now let's do the actual dp on trees plus, dp on trees plus, which is by recursion. Obviously, this is a corresponding tree traversal, which doesn't need to have a base case because this is not technically a tree which has a null node or something of that sort. So we are good with that sense because we're simply taking all the children's. That's it. Now the corresponding recursive check will be check for the node and is parent removed. If it's not equal to -1, simply return it because we have memoized it. The actual fun part starts now. How many edges to remove? That will be determined by, as you remembered, for this specific node, go and check all the neighbors, how many neighbors it had. It has, let's say, 5 neighbors. I have to bring it down to two values. So I have to remove technically 3. But if the parent is already removed, then I need to remove only 2. So this is the edges which I have to remove in my children. Then I will simply go and get these candidates. These are the candidates which are nothing but my children pair of not remove and remove, right? I'll tell you what it actually means, but this is simply because, I will have to sort my children and then take the, if I go back, weight is gone. Okay, yeah, I have to sort my children. If you remember, I have to sort my children. So these are the candidates. These children are actually candidates for me, from which I can actually get my result. So I will go on to, if I go back, I'll go on and put the candidates. I'll go on to every of the neighbor of this specific node. If the neighbor is not parent, then simply compute that for that neighbor, what is the don't remove value, what is the remove value. When I say don't remove, which means that from this specific node to this specific neighbor, from this node to this neighbor, you did not remove that edge. If you did not remove the edge, you will add the weight into your score because you did not remove it, you consumed it. You will add the weight, and if you add the weight, you will also pass in as 0 that is parent removed because parent was not removed in this case. Elsewise, when you remove the corresponding edge between node and the neighbor, then you will mark it as remove, which means there is no weight added because this edge is itself removed entirely, and also mark that, okay, now I have removed this edge. So as I go on to neighbor, his parent will be node and the edge between them is actually removed. Cool. Then ultimately, you know that you have to put all these values in the candidates array because you have to sort in the next step to actually remove these many number of edges. So out of all these candidates, I will simply push the corresponding pair as a don't remove as a node. Then I will simply sort it. Sort on the basis of what? On the basis of don't remove minus remove value. Minimum value of this will come first. Maximum value of this will come in the end. So I will sort my candidates array on the basis of don't remove minus remove, because I know that Now, in the next step, I will have to remove these many number of edges to remove. So out of these candidates, let's say C1, C2, C3, C4, C5. After sorting, let's say this is the state. So if the edges to remove are 2, I will removing these 2 candidates, which means that I will simply iterate on all of my candidates. If my I is less than 2 edges to remove, which means for these, the contribution will be nothing but R1, R2, which means remove contribution I will add. Again, remove is something which you computed here, which is removing the edge from node to neighbor. This thing, you already have this code because this is a recursive call. You'll simply add it. Elsewise, if it is these things, which means you have already taken consideration the edges to remove, now it's your luxury. It's your luxury. In that case, take the maximum from don't remove and add it in your answer. And ultimately, before returning, memoize this step and give back the answer. Cool. I hope you guys got it. If yes, again, this is a very good problem. Not because of it is a DP on tree. DP on tree are usually easy, but because of this case, which makes it tricky. Okay, firstly compute, then find out what, then find out how many, then find out how much is actually the most tricky case. Cool, I hope you guys got it. Again, the complexity for it is pretty simple because you are simply iterating on all the nodes. It's just that you are sorting all the candidates. In worst case, one node can have n-1 candidates, n-1 neighbors. Thus, complexity will be O of n log n. But space, it's a simple tree. We are making adjacency list and we will have n-1 nodes. So the space for that will be O of n itself. Cool, I hope you guys got it. If yes, then please do smash the like button. It takes effort to make all this, and especially along with work. And I'm not saying that other YouTubers don't do it. It's just that it takes a bit of effort to actually build all this and then bring it out. So yeah, again, it's your wish. It just motivates me. Bye bye. Take care.